All right, hello multivariable students. Sorry, ma'am, will be out today. My son is home because his daycare is closed. So today what we're going to do is we're going to look at integrals, double integrals in polar coordinates via a video on YouTube. If you were in class last time, which many of you weren't, we talked about polar rectangles, which you can see here. And a polar rectangle is a polar chunk where it ranges between two theta values. So here we have alpha and beta, and it's ranging between two theta values and two r values, a and b. And we split that polar chunk into smaller polar chunks. And those smaller polar chunks, we found the midpoint. That's what we did here. We found the midpoint of those chunks, and then we evaluated the function at those midpoints down here. So here's the function at the midpoints, and we multiplied it by the area of each one of those chunks. We found the area, that's what we did up here. We found the area of each one of those chunks. And then we summed those up to find the definition of a polar double integral. Now, you don't have to write all of that down. That is all right here in your notes. So this calculation was performed for us by me ahead of time. So you can read through that if you want. But what is most important for us right now is this theorem at the bottom, polar double integral over a polar rectangle, which is what we're going to be talking about today. Now we can actually talk about not just over polar rectangles, but you can see these functions up here in the lower bounds and upper bound of r, which are functions of theta. So you get a polar region like what we have over here on the right-hand side. So this is a polar region between two polar functions r1 and r2. So this is pretty common. We'll see some functions like that. But let's go ahead and jump right in. Now, one key thing, notice that there is an r. You pick up an r when you're integrating here. That's when you convert between, or convert from rectangular to polar coordinates. You have to remember to throw that r in there. In general, that will always be there. That comes from this area formula for each of the polar rectangles is where we found it. So let's go ahead and jump into the first problem here. They give me a double integral of this function 3x plus 4y squared, and they say it's over the region of the upper half plane bounded by these two circles. So upper half plane, let's just go ahead and sketch the region. Two circles of radius 1 and 2. So here's -1, -2. The region, this is the first circle, here's the second circle. We have the upper half plane, and so we are looking at just this chunk. And we want to integrate this function over that chunk. Now, if you try to do this in rectangular coordinates, it would be awful. You'd have to split it here and here, and then you'd have to say this is the top function, this is the bottom function, this is the top function, this is the bottom function, top, bottom. And that would take three rectangular double integrals. They'd all be very nasty and not fun to do. So what we're going to do instead is we are going to convert this rectangular integral into a polar double integral. So here we go. The theta value ranges between 0 and pi. And the radius, of course, ranges between 1 and 2. So we can go ahead and set that up. So here we'll say the integral, let's just rewrite the integral that they gave us, 3x plus 4y squared, dA, is equal to, we'll do r second, so we'll say from 1 to 2, and then we'll say from theta, it goes from 0 to pi. And now remember, x is equal to r cosine theta, and y is r sine theta. Okay, so we'll replace x with r cosine and y with an r sine. So this is going to be plus 4 r squared sine squared theta, and we want d theta dr. Whoops, we have to throw that extra r in there. I knew I'd forget it if I wasn't careful. So this is r dr d d theta dr. I think I put theta first, theta, and then r. Now, the reason that it doesn't really matter which variable that we're integrating with respect to is because we have constant bounds here, theta and 0, or pi and 0. So the constant bounds means that, like Fubini's theorem, you can integrate with respect to each one, either one first. Now here, if you have a function with respect to r, like r of theta, you're going to have to integrate that one first, since the theta integral is going to be involved in the first integral. So the order would matter in that case, but in this case, you can integrate with respect to either variable first, theta or r. Okay, well, let's go ahead and start this integral. We're going to integrate with respect to theta first. The hard one is this one right here, sine squared. What is sine squared? Well, if you remember, last time we talked about the double angle, which is cosine squared. That's cosine 2 theta is cosine squared theta minus sine squared theta. And if you replace the cosine squared with 1 minus sine squared, that's the Pythagorean identity, you will get cosine 2 theta is equal to 1 minus 2 sine squared thetas. And then finally, sine squared theta, if you solve for it from the above formula, you get 1 minus cosine 2 theta all over 2. We'll write it like this, 1/2 1 minus cosine 2 theta. So that is the double angle identity for sine squared. So we're going to go ahead and replace that with a 1/2 1 minus cosine 2 theta. Now this just allows us to integrate a really hard integral much easier. So right here, sine squared is not easy to integrate. So we're just going to replace that and then integrate. So here we go. First integral is going to be 3r, and then the antiderivative of cosine is sine. And then here we're going to have, this is r squared, because we're distributing that r through. And now this next one is going to be plus, let's see, 4 divided by 2 is 2. That's right here, 4 divided by 2. And then we're going to have an r cubed. And then the antiderivative of 1 is theta, and the antiderivative of minus cosine 2 theta is minus 1/2 sine 2 theta. There we go. And the r I distributed already. That looks good. From 0 to pi is what we want to evaluate. dr. Yeah, everything looks good there to me. Let's go ahead and plug in the 0 and the pi. Everything with a sign in it is going to be 0, because sine of pi is 0, sine of 0 is 0. So all of those sine values are going to thankfully go away. And that's just going to leave me with 2 r cubed, this value right here, and then when I plug in pi, I'll get a pi there. And then we need a dr. Plugging in 0 everywhere gives me 0. Yeah, okay, that looks good to me. Let's go ahead and do the antiderivative. Add 1 to the power, divide by the new power. Plug in 2, we get 2 to the 4th, which is 16. Divided by 4 is 4, so we get 8 pi minus, plug in 1, we get pi over 2. And that's going to be, what, 15 over 2 pi? 15 pi over 2. Yeah. All right. So it's a difficult integral. What made it difficult? I think what was difficult about this one was this. Integrating sine squared is not easy, and so we had to replace that. Okay, next problem. Let's go ahead and move on. So find the volume of the solid bounded by the plane z equals 0 and the paraboloid z equal 1 minus x squared minus y squared. Okay, well, let's go ahead and make a little sketch. You don't have to, but the paraboloid is facing down like this, like that. And here is the xy plane down here. So here's the z-axis, and here's the x and y-axis. And so the region that we want to integrate over is down here. This is the plane z equals 0 down here is the xy plane. And we would like to integrate over that circular region. So if I draw a little xy plane down here, the region that we're integrating over is going to be this. If you replace z with 0, in that equation, you find a circle of radius 1, x squared plus y squared equal 1. So that's the radius of this circle. So this is the region R that we want to integrate over. So I was mentioning replacing this with 0. Okay, so that's my region. Now they want us to find the volume, so we have to set up this volume formula entirely by ourselves. They didn't give me any double integral. So I'm going to let theta range between 0 and 2 pi. That's over the entire circular region. And I'm going to let r range between 0 and 1. And what do we want to integrate? Well, we want to integrate 1 minus we want to integrate the paraboloid, so this is really just z equal 1 minus r squared if you replace the x squared plus y squared with r squared, and then we're going to have to do r dr d theta. Okay, there we go. We'd like to do an antiderivative of that with respect to r. Let's go ahead and do that. You could technically split. Notice that this first integral right here has nothing to do with theta. Notice that is the integral is completely independent of theta. So sometimes what you'll see people do is pull theta out like that. This is going to be r minus r cubed. And so then you just really have, whoops, a product of single variable integrals, which is much easier to do. So this one here is just theta from 0 to 2 pi. This one's going to be 1/2 r squared minus 1/4 r to the 4th from 0 to 1. Okay, and this is a product between them. So this is going to be 2 pi. And then plugging in 1, we get 1/2 minus 1/4, or 1/4. Yeah, 1/4. So that's pi over 2. So that would be the volume. So this volume over here underneath the paraboloid, but above the xy plane, should just be pi over 2. Yeah, pretty cool. Okay, let's move on to number 3. Find the formula for the volume of a sphere, x squared plus y squared plus z squared equal r0 squared. Hint, it says find the volume of the upper hemisphere, then double the volume to find the volume of the full sphere. Well, what is the volume formula? We know what the volume formula for a sphere is. That's 4/3 pi r0 cubed. So this is what we're expecting. So this is the answer. Okay, so now what we need to do is set up a double integral to help us find the volume. And let's use the hint. So the sphere looks like this. This is like the previous problem. So this is x, y, and z. Whoops, we put the z in the wrong place. X, z, and y. And then there's technically a bottom half to the sphere. This sphere is radius r0. So this is r0. We're just going to integrate over this region in the xy plane and find the volume of the upper hemisphere and then double it. So this is the region r that we're going to integrate over. So let's go ahead and find the volume. The volume is going to be 2 times the integral. Let's do theta first. Theta ranges from 0 to 2 pi. And next we'll do r. So this is r going from 0 to r0. Now r0 is just some constant. I'm using a capital R0 here because lowercase r is obviously taken as our variable of integration. So capital R0 is just going to be the constant radius of this sphere. It's not changing. The lowercase r, on the other hand, is changing as we integrate over this region. Okay, so what do we want to integrate? Well, let's solve for z. So z is the square root of r0 squared minus x squared minus y squared. Now that's just the upper hemisphere. Now if I replace x squared and y squared, the difference or the sum of those two, that's going to be minus r squared. So we want to replace the inside. We're integrating over this upper hemisphere of r0 squared minus r squared, and we can't forget our r dr d theta. Okay, so that is the hardest part of these problems, is to set up your integral. Once you've got the integral set up, it's just back to calculus, single variable calculus, where you're just integrating. Now, in this case, this integral, again, is completely independent of theta. So this integral right here is completely independent of theta. So if there were thetas in the bounds, then we would have to integrate it in order. But here, we can actually separate these two integrals, bring the theta integral out. And this is just r square root of r0 squared minus r squared dr. Okay, so this first integral is just 2 times 2 pi. Okay, so now this 2, remember, where did that 2 come from? This is doubling the upper hemisphere, so double upper hemisphere. So that's why we have a 2 out in front. Okay. Yeah, so let's do this next integral right here. So let's choose u. We're going to do a little u substitution here, and I will write out the whole u sub. So this is going to be du is just negative 2r dr, which we have an r right there, but we don't have a negative 2. So what we could do is divide by a negative 2 on the outside and multiply by a negative 2 on the inside. That gives us our negative 2r dr. So that's what we want here. So this negative 2r dr is really the same thing as just du. Okay, so let's maybe write that in blue, du. Now what will the upper bound and lower bound change be? So the upper bound is now going to be, if I plug in r0 right here, that's just going to be 0, and the lower bound, if I plug in 0, I get r0 squared. So that will be the change of variables. Okay, everything looks good to me there. So let's go ahead and replace it. So we have a minus 1/2. The integral now from r0 squared, this is u equal r0 squared to 0. And then this is going to be u to the 1/2 du. So the u to the 1/2, that's just the square root of u. This right here is u. So that looks good. Let's go ahead and do the antiderivative. This is negative 2 pi, and the antiderivative is going to be add 1 to the power, divide by the new power. We get 2 over 3 u to the 3/2 from r0 squared to 0. Let's plug in 0. You get negative 2 pi 3, 2 over 3, negative 2 pi, I lost my groove here, 2/3 0 to the 3/2 minus negative 2 pi, 2/3 r0 squared to the 3/2. And what do we get? That finally reduces, this is 0, it's gone. This is going to be 4 pi over 3, is going to be r0 cubed, because the square and the half cancel there, which is exactly what we wanted, 4/3 pi r cubed. So that's the volume formula for a sphere. I'm not exactly sure if that's how the volume, I'm sure that the volume formula was derived some other way, because the volume formula for a sphere is much, much older than calculus. So I would imagine that this is not how it was derived, but it's pretty cool to see the, for example, 4, it says, let me read it. Find the volume of the solid that lies under the paraboloid z equal x squared plus y squared, but above the xy plane and inside the cylinder x squared plus y squared equal 2x. Okay, so apparently that's a cylinder. Let's go ahead and kind of sketch the region here. So here is our paraboloid. Looks something like this. Here's the z-axis, and here's the x and y. And we have a cylinder. So here, this is going to be, if you complete the square, x minus 1 squared plus y squared equal 1. So it's a cylinder centered at x equal 1, y equals 0. So that's right here. And the radius is 1. So let's sketch this cylinder right here. And when it intersects this paraboloid, it's going to look kind of like an oval shape over here, something like that, where it intersects. and that will be the solid that we want to find. Let me highlight the base here. So the base looks something like that. And if you can't visualize that, it maybe will look something like this. Let's see if I can do a better job of sketching it so it'll look kind of like maybe the tip of lipstick or something like that, and this is kind of divoted in there. So this is what we're trying to find the volume of. Let's sketch the region in the XY plane. It's 1, 2, and circle of radius 1, and here is the region R. Okay, great. So if we convert this to polar coordinates, so let's convert this equation to polar coordinates. This is going to be r squared equal to x is r cosine theta, and so we get r equal to cosine theta. Okay, and now that I see that, I remember, oh yes, that's just a circle in polar coordinates to the right of radius 1/2 of this, or diameter 2, so the radius is 1, centered to the right of the pole. The pole is right here. So if I plug in theta equals 0, I get a point right here. And if I plug in theta, so this is theta equals 0. If I plug in a point theta equal pi over 2, this is theta equal pi over 2, I get 0. And if I plug in 3 pi over 4, that's over here, I get this point down here. So this is theta equal 3 pi over 4. And then if I plug in a point right here, this is theta equal pi. So it only takes from 0 to pi to get the correct, to cover the entire circle one time. And then it goes this way, just like this. So it's covering the circle. I've actually plotted this on my calculator ahead of time here. So here we have, if you go to mode, you want polar coordinates down here. There's polar coordinates, and we want to graph 2 cosine theta. And if I change the speed at which this plots, let's change it a little bit quicker than that. We'll say, yeah, that's fine. So that's a slow speed. Now pay close attention to how it plots the graph. It started on the right and loops around going the other direction, and it traces over this circle 2 full times. So what we want to do is integrate over this region once. So we don't want to integrate over through the pole. If you remember from BC calculus, you don't want to integrate through the pole. So what we're going to have to do is avoid that. So what we're going to do is integrate from negative pi over 2, which starts here, and then we're going to integrate all the way through this way through pi over 2. That avoids integrating through the pole there. So let's go ahead and start by setting up our integral. The volume of this region is going to be the integral for theta. This is where we decided theta should go from negative pi over 2 to pi over 2, and then the radius goes from 0, this is r, goes from 0 to 2 cosine theta, So that's the farthest point out on the radius out here. Now, it's really tempting to say that theta ranges from 0 to pi or from 0 to pi. And you want to be very careful there, because you're either going to go over the region too many times, or you're going to get too much volume if you do that. So what you want to do, you could just go from 0 to pi over 2 and then double it. So from 0 to pi over 2 and double that, or you could do like we're doing and go from negative pi over 2 to pi over 2. Now, what do we want to integrate? Well, we want to integrate the paraboloid. So this is going to be z equal x squared plus y squared is the same thing as r squared. So we're going to find the volume underneath the paraboloid. We want an r dr d theta. Okay, let's get to it. Let's go ahead and integrate that. So the r integral here isn't too bad. Remember how we pulled the theta integral out in the previous two problems? Well, this integral right here, notice I can't pull theta past it because theta is involved in this integral. So we can't have that integral, or we can't pull that theta through the integral. So we're going to have to integrate them separately or iterated, one at a time. So this is going to be negative pi over 2 to pi over 2, and then if I do the antiderivative here, I get 1/4 r to the 4th from 0 to cosine theta d theta. Okay, and then we'll plug in the cosine here, so we get negative pi over 2 to pi over 2. Plugging in cosine, we get 16 over 4, 2 cosine, and then cosine to the 4th. Yikes, uh-oh. So that's going to be a little difficult to integrate. We'll just have to muscle through it. But let's go ahead and double the integral and integrate it from 0 to pi over 2. That's because cosine is an even function, and since cosine's even, we can just integrate half of it. It's basically, we're looking at this half of the, if you cut this in half this way, then you have a symmetrical region, which means that we can just only look at half of it and double it. It just saves on the evaluation portion. We have 4 times. Now let's simplify cosine to the 4th. Remember, we have from before cosine squared theta, we're using the double angle here, is going to be 1 plus cosine 2 theta. Remember, sine was 1 minus, so we'll replace this with a 1/2 plus cosine 2 theta, just like that. So let's go ahead and replace that. And that's going to be 4 times a 1/2 cosine, 1 plus cosine 2 theta. That's the double angle. It should allow us to integrate this a little bit easier. And then we'll expand that out. We'll bring out the, this is going to be, the 1/2 squared is 1/4. So we have 2 times the integral 0 to pi over 2 of 1 plus 2 cosine 2 theta plus cosine 2 theta squared d theta. So that was expanding the squared there and simplifying. Now again, this guy right here is going to have to, we're going to have to use another double angle on it. So that's going to be 1 plus cosine, not 2 theta, but 4 theta over 2. Yeah, it's a hard sub, I know. Okay, there we go. So let's replace that to make, because integrating cosine squared is hard. So that's what we're going to have to do. That's the only way that we can munch on that problem. So we get 2 times the integral 0 to pi over 2 of 1 plus 2 cosine 2 theta plus, this is going to give me, let's replace this right here, 1/2 1 plus cosine 4 theta. Okay, and let's go ahead and clean this up. Okay, that looks good. And so now, this is d theta. We're going to get, let's simplify it. We'll bring the constants together. That's going to be 3 over 2 because of this 1/2. And then plus 2 cosine 2 theta plus 1/2 cosine 4 theta. d theta. And now we can finally do the antiderivative. So the antiderivative here is going to be 3 over 2 theta plus, is that going to be a plus? Do I need a minus? Is that formula a minus or a plus? Let's go back and look at sine. Sine was a minus right here. So we want cosine to be a plus. Yeah, that's right. Okay, so this is going to be plus 2 cosine 2 theta. Oh, the antiderivative. Sine 2. The 2 is going to go away by the chain rule or u sub. So here this is sine 2 theta plus this is going to be 1/8 sine 4 theta. Ooh, yikes. 0 to pi over 2. Thankfully, if you plug in pi over 2 to any of those, you're just going to get sines are 0. So that simplifies very nicely. Also, if you plug in 0 into these thetas, you get 0 for sine. So we're going to get 2 times, just the first one here, theta, is just going to be 3 over 2 pi over 2, which gives me 3 pi over 2. Oh, so that's the volume of this weird kind of lipstick shape cylinder. Yeah, interesting. Well, it's not useful to us right now, but at least we can find it, calculate it by hand. It's kind of a toy problem. It works out nice for us, kind of. But at least we got to see this process of using cosine here, the double angle substitution to work on a very difficult power there. The powers of cosine are hard to integrate. Same with the powers of sine, at least the even powers. Okay, last problem here. Let's go ahead and knock it out. So this one, they say, evaluate this double integral where D is the region, it's a circular region between, it's a ring. We actually call that an annulus, although it's x just less than 0, less than or equal to 0. So let's go ahead and sketch the region to get the idea here. X is less than 0, so let's make our x-axis a little bit further to the right, or to the left, like this. And let's go out to 1, 2. We'll go 1, 2, 1, 2. That should be good. So the smaller circle looks like this, and the larger circle looks like this. And we want just x less than 0. So this is what we're looking at, and x less than 0 is only this region on the inside here. So it's a semi-annulus region, I think is what you would call that. So we'll say semi-annulus. 2 n's? I'm not sure if there's 2 n's. Something like that. So this is the region that we want to integrate over. So theta here, we'll say theta should range in between pi over 2 and 3 pi over 2. And the radius should range in between 1 and 2. So this gives us the bounds for our integral for this polar rectangle. Okay. Did I miss anything there? Let's just double check. No, that looks good. So let's go ahead and rewrite the integral. The integral over this region D, they're calling this region D, and this is going to be x plus y dA. Now let's convert this to a polar integral. So theta ranges from pi over 2 to 3 pi over 2, and the radius ranges from 1 to 2, and x is our cosine theta, and y is our sine theta, and we want an r d theta. Anytime you convert from a regular rectangular coordinate integral to a polar integral, you got to remember to do that r d theta. Okay, that looks good. Let's go ahead and distribute the r and integrate with respect to r. You could factor out the r. In fact, let's do that. Oh, the integrals can be separated here. Notice that the bounds on our integrals, let's highlight it here. So these integral bounds are completely independent of theta. Well, excuse me, this integral here is, the bounds are independent of theta on that first integral. So what that means we can do is we can factor out everything that is not involved with theta. So this is going to be pi over 2, 3 pi over 2. Let's just rewrite this. If I factor out the r squared, there's an r here, and then these both have an r, then I'm left with cosine theta plus sine theta. And then we have a dr d theta. And now we can bring this, this d theta past all of this here, as well as the sine theta, cosine theta. We'll bring that through the r integral because it has nothing to do with r. So this is 3 pi over 2, and then we have cosine theta plus sine theta d theta. And then we're integrating from 1 to 2 of r squared dr. Okay, that looks good. Let's go ahead and do these. Now these are being multiplied. These two integrals, there's a product between them because there was a product right here between the r squared and the cosine theta sine theta. That looks good. Let's go ahead and do the antiderivative. Here this is going to be sine theta minus cosine theta. and we want to evaluate from pi over 2 to 3 pi over 2, and this is going to be 1/3 r cubed from 1 to 2. Okay, we'll evaluate both of those and multiply. So plugging in 3 pi over 2, sine is -1, and plugging in 3 pi over 2 into cosine, that's 0, and then minus plugging in pi over 2, sine is 1, cosine is 0. Okay, and then we want to multiply that by plugging in 2. We're going to get 8 over 3, and then plugging in 1, 1 over 3. So we're going to get a total of -2 times 7 over 3. So we get -14 over 3. What an ugly answer. Now, this doesn't represent necessarily a volume, and if it did, it would be a volume below a curve. So it's still, it's below the curve on average because it's negative there. So this particular problem, they didn't speak about this region as some particular volume. It could be some value that we're interested in. But yeah, there we go. So we did some clever integrals here. This one was pretty tough. This formula, these conversion formulas, you're probably going to want to know. You're going to see those again, maybe on a quiz or something like that. But until next time, I will see you guys, let's see, on Wednesday. Yes, I'll see you on Wednesday. Yeah, all right. Well, I'll see you then.